Okay, folks, I'm gonna go ahead and get started. I am going to be a little bit challenged today. Basically, my iPad, I'm not certain why it's not charging. I've got the cord plugged in, it's just not charging. So I've got to figure that out. So I'm gonna do what I can until it dies, and then I'm gonna switch over to the main computer so that I can continue. But if you watch the video later, you're gonna, at that point, there's not gonna be any more. It's just gonna be writing. There's no vocal capability on that. So it's a bit of a disadvantage. I can't do anything about it. I'll do the best I can though. So I wanted to just recap a little bit of what we talked about on Tuesday of last week. So the law of conservation of energy says that energy cannot be created nor destroyed. So when we're thinking about a reaction, we have to think about it from the perspective of the system, which is the physical reactions, the reactants, and the products. And then the surroundings. The surroundings is everything else, including the water that it is dissolved in. The container that it's held in, the air above it, stuff like that. Now, when you add energy into the system, it's going to have a positive sign because the system's energy is going to increase at that point. If energy leaves the system, it's going to have a negative sign because the system's energy is going down. So the sign does not mean positive, negative like it does in a typical mathematics course. What it does is it indicates directionality. Energy is a state function. Basically, what it means to be a state function is it's a function that depends only on the initial and the final conditions. It does not depend upon the path that you take to get from the initial conditions to the final conditions. Therefore, the energy of our system is going to equal the energy that went in minus the energy that went out. So in other words, that change in energy that occurred to the system itself. Now, for a reaction, when we talk about energy of the system, we can talk about anytime we see a delta, really, that delta means final minus initial. So in a reaction, that final is going to be the product, the initial is going to be the reactant. So delta E for a reaction is going to equal E of the product minus E of the reactant. Now, the part that I told you that you needed to go ahead and read, you need to watch the videos from last week if you have not, because there is a lot of information that is in those videos, in the video lectures that I did not take time to cover. But I will do a little bit of that at the moment. So when we talk about the energy of a reaction, again, it is a state function. Energy is equal to Q plus W, where Q is equal to the heat of the reaction, and W is equal to the work that the reaction performs. Q and W are not state functions, so they are not dependent, or so they are dependent upon the path that it takes. Now, Q, the heat, can be calculated using impact, where M is the mass of the material, C is the specific heat capacity, and delta T is final minus initial for your temperature. C being the specific heat capacity for the substance. Basically, folks, every single substance out there can absorb a certain amount of energy before 1 gram of that substance changes by 1 degree Celsius. For water, the amount of energy that can be absorbed is 4.184 joules of energy before 1 gram of water is going to increase by 1 degree Celsius. As I mentioned on Tuesday, that's why a watch pot never seems to boil, is because it takes a lot of energy in order to increase the amount of water in a pot of water to a temperature so that it just increases by 1 degree Celsius, much less more than that. And then when we think of our the energy diagram that I showed you at the beginning, again, system and surroundings, in order to follow the law of conservation of energy, you must always think in terms of system and surroundings. So when we think of heat, the heat of the system is going to equal the heat of the surroundings. The value will be the same. The only difference will be the sign. Because if one is increasing, the other one has to be decreasing. So now there was another piece to that that I did not go over on Tuesday, and that is the work factor. Again, if you look at the change in energy, the change in energy is equal to the Q plus the W, where the Q is equal to the heat and the W is equal to work. Now, we really didn't talk about the work point. Relatively speaking, the amount of work that a chemical reaction does, unless there's a lot of gas involved, the amount of work that a reaction performs is going to be very minimal. The main thing is going to be heat, but you can't just completely discount the work. So work in a chemistry experiment is going to be pressure volume work. How much pressure does the reaction apply to the surroundings? And what is the volume change that occurs on those surroundings? Because the system is losing that energy and it's applying pressure to the surroundings, that's why it's a negative P delta V. So again, if we're going to really talk about the energy of the reaction, we've got to talk about the heat of the system plus the work that's done by the system, where the work is P delta V work. Now, if we're talking about a liquid, a solid, or aqueous solutions, the amount of pressure and volume change is going to be negligible to zero. Or if you're talking about a bomb calorimeter, the amount of pressure, the amount of volume change is going to be negligible to zero, which means that the work piece becomes zero, and so the energy of the system is simply equal to the Q of the system. Because that delta V is equal to zero, because they don't change much. A liquid is not going to change its volume by any grand amount. Now, however, when you're talking about gases, the generation of gases apply pressure on the system. I mean, that's what drives your vehicle, is the combustion of octane to form CO2 and water. Once you produce a lot of gases, those gases are going to apply pressure to the system. It's gonna, that applied pressure is gonna cause a change in volume. And so we wind up having to say that the energy of the system is now equal to Q of the system minus P delta V. In other words, we actually have to take into account that work factor when we're dealing with gases, or when you're dealing technically with a coffee cup calorimeter. Now, if I rearrange this equation, I get energy of the system plus P delta V is equal to Q of the system. And then when we do that, that means that it comes out equal to the enthalpy of the system, which is what we're really focused on in this particular chapter, is the heat capacity and then the enthalpy. Now, again, the energy and the enthalpy are going to be very, very similar unless there is a lot of gas formed. If there's a lot of gas formed, they're not similar. But if you'll notice, I used a capital letter for both energy and enthalpy. That is because both of them are state functions. Again, that means that they're going to be dependent upon the starting material and the ending material, but it does not matter what path you take in between. Oh, wrong computer. And this kind of catches us up to where we were on Tuesday of last week, without all the problems that I did in between. with just a new piece of information, which is that the enthalpy is, you do have to take into account that work factor if you're talking about a large quantity of gas being formed. Because then you do have to worry about pressure volume work. Any questions? What we're going to do today is, number one, we are going to look at where the energy comes from for a chemical reaction. The second thing we're going to do is we're going to apply the rules that we learned about enthalpy on Tuesday to Hess's law. And the third thing we're going to do is we're going to start with enthalpies of formation. Now, I wanted to make sure I got through this before in case my computer timed out, my iPad timed out. I want to take a moment and take a break and actually discuss what's going down the next 2.5 weeks. So this week is going to be the last week of new material. We are going to finish up our discussion of enthalpy, hopefully today, but we will finish it up this week. And then we are also going to do the gas law chapter. Now, with respect to the gas law chapter, number one, I plan to focus on my attention on that Thursday. But if I can't get through all that information Thursday during class, then I will pick up and finish that information in lab. So come prepared for a lecture to start lab, because I will finish up all new information this week. On Thursday, the lab is a gas law lab. It's actually a pretty quick lab. There will be no quiz, but we will be doing the gas law lab. And that gas law lab is due next Tuesday at the start of our class, because next Tuesday basically is our last, next week is our last week. Yes, I know. Next Tuesday is your 4th exam. On Tuesday night and Wednesday, I'm hoping nobody really bothers me, because I'm going to be in a grading frenzy, because my goal is by Thursday for you to know exactly where you stand. That way you can decide whether or not you need to take the final. Which is the following Thursday. So next week you have an exam on Tuesday, and then on Thursday my plan is to discuss how to study for my final for those that need to take my final. And that, folks, is a general overview of everything that is to come for the rest of the semester. Any questions? I'm currently in a grading frenzy, trying to make sure all of your grades are in. The attendance points will vary slightly once I get those added in, but that's pretty much it. So I'll have most everything else uploaded so you'll know where you stand. Any questions? Okay. So this thing is going to die, so I'm just going to stop broadcasting. And I am going to leave.